Hey guys, how's it going? Today we're gonna be talking a bit about complex numbers in linear algebra. So basically, I'm gonna change your perspective of what you already know about roots of equations and apply it to the complex plane. Let's get started. So I'm gonna start off with a relatively easy example. Z to the power of 4 minus 1 equals 0. Now, even without doing anything, you can already tell that this is z squared minus 1. Z squared plus 1 is equal to 0. Like, you don't need a genius to tell you that. And then you can just say z will equal plus or minus 1 and plus or minus I. Pretty straightforward. But I want to talk about a general way using polar coordinates. So then in that case, z to the power of 4, let's call this w. And let's say that that equals 1. Okay. Now, z to the power of 4 equals w equals 1. And now w equals rei theta. If you were to put graph 1 on the complex plane, it has an angle of 0, and then it's just equal to 1. But I'm going to mix it up a bit. So I'm just going to say, I'm not going to say 1. I'm going to say e to the power of 2 pi I k. Because every 2 pi I, it goes back to the same location. W is equal to e to the power of 2 pi k I. Now, z, remember z to the power of 4 is w, right? So z is equal to w 1 over 4, which equals e, and then the exponent is divided by 4. So pi over 2ki. And then k ez, like k is any integer. But we only consider, technically a equation has infinitely many roots, but there's only a certain amount of distinct roots. So here it only has 4 distinct roots. So z, you can even say zk, for instance. So z0 equals, and then if you put k equal to 0, that's just 1, or like e to the 0. Z1, replace k with 1. E to the power of pi over 2i. And when you use Euler's formula, you just get I. Z2 is equal to, let's see, so that would be e to the power of pi I, which is -1. And of course, C3 equals e to the power of 3 pi over 2i, which equals -I. And thus we proved it. Let's try another one. Let's find all the square roots no, sorry, not all the square roots. Let's find all the roots of 8 to the power of 1 over 6. How do we do that? Say W is equal to 8. Then when you say that REI theta, it equals, that would be 8. We're still on the 0 part, so that would be E, and then E to the power of 2 pi ik. Now, Z to this equals W equals 8. So then Z, then that's our answer, what we want, is equal to W to the power of 1 over 6, which equals 8 root 6. 8 to the 6th root, that's just the square root of 2. E pi over 3 ki. Because 2 pi ki over 6 gives you pi over 3 ki. I'm going to put a k here. Z0 is just square root of 2. E0, which is the square root of 2. Z1, square root of 2 e to the power of pi over 3i. Which is cos pi over 3 plus I sine pi over 3. Cos pi over 3 is 1/2 plus I sine pi over 3. 2. Z2 is equal to root 2 e to the power of 2 pi I over 3i. Cos 2 pi over 3, negative 1 over 2, plus I root 3 over 2. Okay, let me think. So that's just pi I e to the power of pi I, which is negative root 2. Z to the power of 4, or sorry, Z4 is root 2 e 4 pi over 3i. Cos 4 pi over 3, so you get root 2, then negative 1 over 2 minus I root 3 over 2. Yeah. And Z5 is equal to root 2 e 5 pi over 3i. root 2, 1 over 2, minus I root 3 over 2. And those are your solutions. Okay, one last one. Let's switch it up a bit. Let's switch up the angles just a bit. So far, we've only been dealing with the real numbers on the axes and such. What if we involved something that had complex elements to it? Let me go. Okay, here is the very last one for today. -8 minus 8 root 3I all to the power of 1 over 4. Let's find all the roots of this. So just first of all, say W is equal to -8 minus 8 root 3I. And if it helps, just draw that on this diagram. This is a rough sketch. It would be somewhere here. And just label this W. And R would equal the a squared plus b squared, which when you calculate that out, that would be 16. It's 8 squared, square root of 8 squared plus 64 times 3 is 250, square root of 256, which is 16. And then theta equals, so 8 tan inverse of tan inverse of root 3. But since we're on the third quadrant, since they're both negative, which is 4 pi over 3. Okay, so now R E I theta, because W is R E I theta. R E I theta. That is 16 e to the power of I 4 pi over 3. But we need to do this plus 2 pi k, where k is E static. Okay, so that is what you do there. Then Z, you have to do this equals W to the power of 1 over 4, which equals 2 e to the power of I over 3 plus pi over 2k. I'm just going to zk here. So z0 is equal to 2 e I pi over 3. Which equals 2 Cos pi over 3 gives you 1 over 2. And sine pi over 3 gives you root 3 over 2. Should I simplify this? Yeah, sure, why not? Which is 1 plus root 3i. C1, and it's just same process over and over again. 2 pi over 3 plus pi over 2. Pi over 3, okay, so that's 2 pi over 6. 5 pi over 6. Which is equal to 2 cos of 5 pi over 6 gives you, let me think. Cos of 5 pi over 6 gives you negative root 3 over 2 plus 1 over 2i, which is equal to negative root 3 plus I. Z2 equals, let me think now. So Z2 is 2e, okay, so pi over 3 plus pi is I 4 pi over 3. Which equals 2, and then you're gonna have 2 both. So let me think. Cos 4 pi over 3 is negative 1 over 2 minus root 3 over 2 I, which is negative 1 minus root 3 I. And one more. C3 is equal to 2e. Okay, so pi over 3 plus 3 pi over 2. So it's 9 over 6. It's 2 over 6, 11 pi over 6. Which is equal to 2. Okay, so cos 11 pi over 6, that's just root 3 over 2 minus 1 over 2i. Which is root 3 minus I. Those are all your roots. So hopefully I taught you a bit about something about roots and, finding the roots of an equation and how you can relate that from the simple plane to the complex plane. I hope you enjoyed this video, and I'll see you guys next time.